I wanted to say thank you to Michelle, Heather, and T-Mobile for helping put this together. And I'll hand this over to Julianne.
Yeah, I'm hearing an echo. Not sure if we can get a mute check.
Yeah, I heard this too.
It might just be when we're talking. Yep. All right, I'll share my screen. Can you see my screen?
Yes.
You might be getting. I'll just do this. So a little bit about me. I am from Texas originally. Sorry, that it's just really distracting. The echo. That seems better. Okay. I'm from Texas originally. I moved to Washington, to Seattle area to work for T-Mobile about 4.5 years ago. So I've been working with T-Mobile in the EDS team, the Enterprise Data Solutions team, which is in our greater IT organization, now product and technology, for 4.5 years. So I've worked on projects related to new billing platform, supply chain logistics projects, and most recently I worked on the Sprint merger, specifically on supply chain reporting and BI and advanced analytics around the merger. I started my career as an analyst out of college. I didn't have any previous IT experience. I majored in pre-med, so had pretty much no experience in computers or IT. And joined as an analyst, and I now I'm a product manager, technical. So I help drive roadmaps. I work on as a project manager, sometimes sort of doing whatever it takes to get business value delivered is how I kind of describe my role. I recently graduated on Saturday, actually, from the University of Washington, Masters of Information Management, with focuses in BI and data science. And I've been learning data science in classes and on my own. I recently changed in our EDS team from more traditional canned reporting, data warehousing. I've moved into the advanced analytics team called SIPS, Cognitive Intelligence and Platforms. So we are more focused on advanced analytics problems and providing solutions to the larger business teams for solving advanced analytics, machine learning, operations research, that kind of thing. This is just a cheesy slide that I put together from photos from my phone or over the last few years, but a little bit about our team. So Enterprise Data Solutions, we're about 250 full-time employees and growing, and we support any and all things data. So probably our biggest, the biggest thing that we support is data warehousing. A lot of business teams will source data from our data lakes, data marts, data warehouses, SQL Server, Teradata, Hadoop. We kind of support it all. We do data platforms. We have platform as a service, data as a service, infrastructure as a service. So we offer all of these types of services. Like I mentioned, data lakes, we have Hadoop, we have AWS, we have Azure. We do data visualization, so reporting, we have Tableau, Click, and Alteryx, kind of you name it, we support it. We do financial reporting, so this is anything from SOX compliance type reporting to posting things to the general ledger, to reconciling systems, even subscriber reporting that goes up to the CEO and the C-suite every day for them to make critical business decisions. We have those reports coming out of our systems. We support CCPA, so the whole CCPA implementation for the enterprise is under our team. We do data governance. We have an enterprise-wide data governance platform that we're rolling out called Edge, that's supporting where do I get my data, where is it located, not just in our EDS systems, but across the enterprise. Customer 360, machine learning, operations research. We have an event every year called Datapalooza, where we host a hackathon, data hackathon, and we do operations. We have some applications that support operations around transportation and warranty, device warranty, and things like that. And our slogan that I just love is, we model for a living. This is just a blueprint of what our advanced analytics system supports. You'll see that there's quite a bit here that we support. Anything, like I mentioned, from data virtualization, data visualization, feature engineering, compute, trainings. We do trainings. We have data scientists on our team who are putting together training sessions for the enterprise. It's sort of anything related to serving the enterprise with data, with platforms, is what our team supports. So that's just a little bit about me and what our team supports within the larger organization and within product and technology at T-Mobile. A lot of data and a lot of magenta. I'll stop sharing and pass it off.
Did anybody have any questions for Julianne at all?
Oh yeah, good point.
If not, we could move on to Heather.
Can I ask a question?
Sure.
So your team serves, I should say, provide solutions. Is that on-prem, or is it also for cloud solution, or both?
Both, yep. We support, so we have Teradata boxes that are on-prem. We have Microsoft SQL servers that are on-prem. So we support everything from the platform all the way to data, data architecture, enterprise data warehouse, and reports. So sometimes the business will come to us and say, we need a report built for us. We'll do the data integration, the data ingestion, all the way end to end until we give them a report. Or they might say, I need a platform, or I need access to data, and we'll point them to data. So yeah, we support on-prem and in the cloud. We have Azure and AWS that we support for on-cloud.
But then T-Mobile act as like integrator, which is like they will hire different vendors for different part of the solution and then combine everything and propose that as a solution, right?
I'm not sure I understand the question. Are you saying we have contractors?
If you want me to try.
Sure.
So it's a combination of both. So we do have things that we buy and host and figure out how to work with those. Some are from vendors. And we also do have things that we build completely internally, and we support those as well. So it's like a combination of everything. The enterprise philosophy is, if another company can do it better and they've done it first, and then that's fine. If not, we will build it ourselves, and we will build it correctly.
Okay, thank you.
Great answer. Yes, that's how our team operates. Generally, so our goal over the last few years has been to build data for the business. We're sourcing data from literally thousands of data sources. Just within supply chain alone, we have 1,000 source feeds coming from probably 100 different sources. So it's it's pretty expansive, all the things that are supported from a data perspective. And if you think about, there's not really a one size fits all answer. And we very much take the philosophy of, if we can deliver business value however we can, we'll go with it.
Thank you. And congratulations on your graduation.
Thanks. It's been a long time coming.
All right, we'll hand it off to Heather.
Great, thanks.
Thank you.
Okay. Bring the presenter. Okay, and then I will start to share my stuff. Can you see it?
Yes.
Awesome. Because yeah, cool. Okay, so I am Heather Nolis. I am a machine learning engineer on the AI at T-Mobile team, and I've been with T-Mobile since 2017. I started as a summer intern, actually, and then I liked my team so much that I decided to never leave. So I joke that I have the longest internship ever. I think my internship was technically almost 2 years, because I was like, I'm never leaving. This team is the best ever. I'm sticking here. But I was in my former life, I believed I would become a neuroscience PhD. And so I kind of did the same transition from biology over into data land. The thing that got me wanting to do this was I took a bioinformatics class, and it was a lot of string processing in Python and building Markov models to tell where genetic deletions and insertions happened. And I was like, man, this is the coolest. Forget biology. I'm on this computer stuff now. I'm extremely active on Twitter. But if you have like a big question and it's more serious, it's better to reach me at my work email address, because, you know, I'm obligated to respond there for professional integrity, whereas on Twitter I can do whatever I want. Let's see. Okay, so this workshop is called Deep Learning in Production, and it's like, you think that you're going to teach me all of deep learning and all of API development and all of cloud computing in 2 hours? No. Nobody could do that. That's like 4 separate PhDs in one, right? So what are we actually? What is my goal here in the next hour and a half? And it's basically, it's unreasonable for any one person to know everything that is compacted in the stuff that I'm going to teach you, because it was created by a giant team of professionals who all have specializations. So if I throw out things and you've never heard of them before, that's super, super fine. It's unreasonable for everybody to be a data scientist, an enterprise architect, a software engineer, also a deep learning master who knows R and maybe some other languages and Docker and Google Cloud. Like, never, ever, 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 ever gonna happen. And so my goal here is to show you what you don't know about how my team builds APIs and give you a project template that you can follow to do it yourself. So that way, if you find anything that you don't know that you want to learn more about, now you know what you don't know. And so the rough agenda is I'm going to give you the quickest introduction to deep learning of all time, just to level set. And we're going to talk about how my team specifically uses deep learning and why I think it's really powerful for our use case. Then we're going to train a neural network that can generate pet names, and we're going to do a code walkthrough of an enterprise style project. So it's basically like a play version of exactly what the code in our enterprise Bitbucket looks like. And then we're going to deploy it to Google Cloud. And all of this can be found in GitLab. So there's the repo. It should be public. If somebody could type it out and put it in the chat, it would be awesome. Because you can go there and you can clone it, and you'll have all of the code that I'm going to be talking about and all of the beautiful documentation that's been written there at your fingertips, as well as this PowerPoint deck. And so with that, I'll begin. But like I said, we're going to create a neural network that names pets. And so I Googled for the cutest pet of all time and got this little bitty hedgehog. And the neural network named him Jojo Pet. I think that's adorable. Going to be building. So deep learning is kind of intimidating. So to make it a little bit less intimidating, it's really great to set some expectations, like really level set, like what is deep learning? Neural networks of some sort. Neural networks they're a technique from the mid-20th century, and they were really academic. Like, there was no real practical way to do neural networks that felt good to anybody at scale. But now it's feasible because we have GPU processing, which allows you to make this neural network computations very, very quick. So finally, you can see what a neural network would be doing, and you're able to actually do it instead of just academically pontificating on what if we could make a neural network. And the thing that made, well, there are two things that made deep learning less intimidating for me, and one of it was just realizing that architecture, by and large, is trial and error. If you want to know what layers need to be in your neural network, you look at what other researchers have done, and then you start playing around with it yourself. And I was like, oh, you mean I'm not just supposed to be some math wizard that can sense in my brain exactly how all of the layers should be positioned? I can just experiment. Great, I love experimenting. I hate being a magician. And so why is deep learning popular right now? Well, because with some older learning algorithms, the performance does not increase as data begins to increase, but we are living in a world where data is logged all the time. You just heard Julianne talk about how much data we have at T-Mobile. To truly take advantage of the volume of data, we need to be using whatever algorithms can take advantage of that data the most, and frankly, that's deep learning. And so this is one of my favorite examples because I remember when this image was posted, this XKCD comic, saying that if you wanted to do image recognition to define a bird, it would take 5 years and an entire research team. And then in 2018, Google could already do it. And that's because of deep learning. We never anticipated deep learning suddenly being feasible, but it rapidly became feasible before the 5 years and the entire team would have even completed it. And so machine learning is really cool again. It gets people really excited because now finally it's practical. And so this is an oldie but a goodie meme, and it says, is this AI? And it's the marketing team labeling a linear regression as artificial intelligence. This is something that's been done. My favorite example of artificial intelligence was one time the company Sprite was like, I am going to use AI to decide what the next Sprite flavor should be. And they spent tons of money and did tons of research. They got a bunch of data from those machines that you pick out of like 100 different sodas. And what their AI said is that they should make cherry Sprite because that was the most popular flavor. First of all, that's not AI, that's a count function, right? They just counted up what's the most popular flavor. But then the second thing is that any marketing guru walking through Target could have told you that the most likely flavor that Sprite should make is cherry Sprite because cherry 7-Up has existed since the 80s. So if you call your linear regression AI, it might get funding. You might decide to use a neural network to tell you that you just need to make cherry Sprite. And so that leads to my team. I say when you slap AI on things, it gets funding. My team is the AI at T-Mobile team. Because when you slap an AI on it, it works out well sometimes. And what our scope is customer care. Our goal is not to understand anything about individuals. Our goal is to build intelligent software that can help our call center agents respond to you most quickly and most effectively in the shortest amount of time. So like little helpers. The description we always use, which is kind of cheesy, is we want to build Jarvis so that way every single one of our agents can become their own little Iron Man and have all the technology that they need at their fingertips, every source of information, so that way they can solve their problems the quickest. And so yeah, this is why is deep learning now easy? Well, because we have GPUs. Keras exists, which even makes TensorFlow easier, which is now wrapped back into TensorFlow. But modern tools mean that you can do this very quickly. And we use this deep learning in our product Expert Assist. And so how Expert Assist works is it's very simple. If you have a customer, say, type into T-Mobile via like Twitter, they DM T-Mobile on Twitter and they say, I'm traveling to Europe and I need my phone to work. What we want to do is before the agent even looks at the message, say, this is a conversation about unlocking your phone, go out and pull up all the information about this actual customer's phone, and then retrieve insights about from our internal knowledge bases. So there are several different models that run there, but there's an information retrieval, there's a classification, and then there's just the getting the facts to the agent as quickly as possible. And this stops them from having to go into 4 different systems and figure out what's going on, again, before they even see the message. So we're setting them up for success and hopefully setting the customers up for a really great experience. And so how this works is we classify the message immediately. And so when they send us a text message, we say, I see that you're looking and this is a bill breakdown message. And so how can we present that to the rep and then also use some customer care signals to help inform that intent? So like if somebody has a really poor signal and they've had a lot of dropped calls recently, there's a higher probability they're coming in to talk to us about the network, which was really bad where they are. But if somebody just upgraded their phone and it's super great, we see everything's working well, maybe they're calling to upgrade the second phone, which is also eligible. So there's a way that you can pull in all these features that aren't natural language and just throw it into the deep learning and let it figure out all the feature engineering. So we do this using R, Keras, and TensorFlow. Wow. Pop up. And we actually use a convolutional neural network that looks at buckets of 5 words and then does a classification on each of those groups of 5. And then it classifies it into 88 different topics depending on who you're talking to. And we open sourced this after we figured it out because it turns out that nobody had really done deep learning APIs in R before. And so a little over a year ago, we released this architecture that we did to make these deep learning models and be able to have them run and serve over 2 million insights a day, hopefully growing to 5 million. We have a project underway. So we made it open source because I wanted other people to play with this and I wanted other people to see how easy it is because the first data scientists on our team didn't quite understand the vision that I had. And the code is very dense. If you're not a software engineer and you're not a data scientist, it probably sucks to read. But hopefully this workshop will give you enough of an intro that if you wanted to use that open source project, it would be highly available to you. And so what we're going to build here, it is a pet names generator. And I say because deep learning doesn't have to be serious. I always learn the best whenever my projects are very fun. And so this is a project that my wife and I did on our own to practice our deep learning skills. And that I shared it with you in an enterprise fashion. And so what we're actually building, their goal is to generate adorable new pet names using the City of Seattle pet license records, which are just freely available. And if there's any sorts of this data for wherever you live that you want, you can do a Freedom of Information Act request, get the data yourself, and then you have very interesting data sets to play with once you start looking at public records. It's because it's okay for technology to be fun. And so the images here, I have You Look Like a Thing and I Love You, which is one of my favorite books about how artificial intelligence can get really silly and weird at the edges, and sometimes right in the center, honestly. There is, if you look there, those are neural network generated Pokemon. And then the Mr. T thing above was a neural network generated escape room themes. And so it says, Mr. T has provided you with a clock to aid your effort. Click it, switch it, move the light, and stop feeding the pigeons, which is super silly, makes me happy. So, and what I want to say is don't worry about what you don't know. If you're not very familiar with deep learning, it's easy to look at one of these architecture models and get really, really intimidated. And the second thing that made deep learning click for me was realizing that each of those nodes is just like a little bitty linear regression, you can say. And what we're doing is still taking an X's and predicting Y's. I'm still defining my target. I'm still making my data set. And so when you understand that you're still taking X's, predicting Y's, and the architecture is actually very trial and error. It's like, okay, I have a space to experiment that's much safer than the big, scary academic articles that you read about deep learning, and it becomes way more tangible, at least for me. So this is to train the pet names generator. And this code is available on the repository, and this is the trainmodel.r file. And so the easiest way to train the model is to just open the R project, hit train model, and go. The model to train on my local machine took 50 minutes, and there's no way that my local machine could do it while I'm also streaming WebEx. So if you wanted to start that now, by the time that you're done here, you would have a model running. If not, I've included a model in the repository already that I trained this morning. And so I think it's one of the ones that I've trained in the recent past. And so you can just load that up if you don't want to wait 50 minutes. But I still think it's really important to understand what the code does. That's why we're here. So yeah, over here we have all of these pets are neural network names. So this is Squeezy, the German Shepherd. And so, So the first thing when you look at the trainmodel.r file, you'll see it's very basic model stuff. You are loading the libraries that you use. We're loading some parameters from a file that I've defined, and I'll show you those in a little bit. But Okay, easy peasy. Oh, those slides are out of order. Anyway, and then you need to load and clean the data. And we don't need most of the columns that come in the CSV that's included, the CSV of the Seattle license plates. And so again, I'm going through this super quickly, just so that way when you look back over it later, you can understand I don't expect all of this to click. But what we're here is we're loading the data. We're reading it in, we're removing anything without a name or a species, we're making sure that there are no weird characters, we're making sure it's all in a format that our computer really likes, and that there's all of the excess is thrown away because, as you know, neural networks are really computationally intensive, so why have features in there that you don't need? And then we need to create subsequence data. So since we're generating a pet name, what matters is not only what letter you're on, but also all of the letters that have come before it so you can predict the next letter. So I use the neural network generated name Bloxy. And so the subsequences for Bloxy would be B, BL, BLO, BLOX, BLOXY, and BLOXY plus. Plus is a random character that we picked that was not in the cleaned data, just to designate the end of a name so that way the neural network would know, okay, I can stop predicting the next letter now, that was the final letter. Generate the subsequence data, we shuffle it around, and then we create the training data. And so this is all things that you know how to do. If you can create a logistic regression, you can do every step that I've mentioned so far. And so the name data is a matrix. We need to make sure that we have the last character there, and we need to make sure that we are one-hot encoding the information. So what this means is computers don't understand words. And if you do NLP, you know this, but if you don't do NLP, then you don't. And it's computers don't actually understand words. To get a computer to understand words, we have to convert them all into numbers. And so what we do here is we change each character into a number. That's a number 1 through 26 through the alphabet, just wherever it is. So B is a 2. And then we change all of those into a 26-dimensional array that has a 1 wherever that number was. So that way we can tell in just ones and zeros, and the quickest way possible, was this letter a B or not? Was this letter a C or not? And so a 1 in the array means yes, this letter is present, a 0 means it's not, and you'll only ever have 1 in one 26-letter array. So then we split it, we create the test matrix, and we create the Y matrix. And then we define the neural network. And again, this is all trial and error. So this is literally, we just took something off the RStudio website, tweaked it around a little bit, and found out how it works. For my job at T-Mobile, because we deal on customer conversations back and forth with representatives a lot, those conversations don't really change, and the way that you classify it doesn't really change. So tweaking our architecture, we have it pretty much down, and we never have to think about our neural network architecture because we've already put in the work of figuring it out. So here we've done the work of figuring it out for you. It's pretty easy. There's an LSTM, which is a useful technique for predicting sequences. You have a dropout rate, and what the dropout rate does is it kind of helps you overfit. It says anything that you've learned, the dropout rate of 2 says anything that you've learned, forget 20% of it, because you don't want your neural network to be too good at what it does, because then it's not very funny. We take a softmax, and we actually compile the model together. And then you train the model and you save it. And like I said, this on my local machine took 55 minutes the last time I did it. And that's about average. And so if you have a really fast machine, and this is all with CPU, I'm not using any GPU to train anything. But so if you have 55 minutes, you can do it. If you have just a very good computer, it might go more quickly. But 55 minutes is just about right. And what we have here, if you look, the batch size, again, configurable, doesn't super matter. And the epochs down at the bottom is how many times the neural network actually loops through the data. So it loops through it all, it forgets 20%, it loops through it all, and it forgets 20%. So that way it can kind of generalize a little bit is what we're trying to get it to do. And then we save it as an H5 file, so that way we can easily load it later. If you don't save it, it would take an hour to start this process every single time. So saving the model is really important. So far we've learned how to, or we've seen how to, I guess, read in the Seattle pet license data from a CSV, clean it, and you drop most of the columns. We've created the appropriate training data, which consists of subsequences of names. We have trained the model, and we've saved it. And now this is the part that I like the most, which is preparing it for production. Getting data scientists work off laptops is really my passion. People build beautiful models constantly and they have no idea how to share them with the world. And that's what we're about to do. But first we have to go over some engineering fundamentals, because if I didn't tell you what all of this stuff means, it wouldn't feel cool when you finally do it. And so what does it mean to put something into production? Putting it into production is when I am able to get the code off of my machine, so that way other people can interact with it whenever they want. And so we talk about A data science and B data science sometimes, where A is analysis, and you're analyzing data to provide a result, and that result normally goes to like inform a decision. And B data science is you're building models so that can continuously run. And that's what we want to take this from. We've done an analysis, we've decided that our pet names generator is good enough, and now we are building it, and we are deploying it. We are getting it off our local machines so that way people the world over can name their pets ridiculous pet names based on our neural network. Which, as an aside, when we first did this project, I tried to shop it around to several different humane societies in the area, and none of them quite got it. So nobody took us up, but I was like, look, you don't have to name your pets anymore, and it'll be really funny. And it was nobody liked it that much. I think people like giving their pets a personal name more than you anticipate. So yeah, we're going to put this pet name generator that we defined the model for into production. We're going to do that using APIs. And so APIs, I think that most engineers wouldn't even know what API stood for, so you don't really need to know it. And specifically what we're going to use is a REST API. Most of the time when engineers say APIs, they mean a REST API. There are other types of APIs, but they are super modern, no one really uses them. And there are only really two methods of interaction that we're going to focus on. We're really going to focus on one, but there are two major ones. There's GET, which is how you tell a computer far away, give me this thing I want. And there's POST, which is how you tell a computer far away, I want you to have this thing. So GET, POST. And we're going to be focused on getting, because we're going to want to get pet names from the cloud computers. Okay. And so a GET request in this simple example is, what if you had a location, or what if you had a thing on your phone to tell you the weather? And you wanted to get the weather from a website. So what the code must do is it must convert the input variable so R can use it. So it might be taking in your latitude and your longitude to find your location. It needs to run the model to make a prediction, which is some computation based on where you are, what it thinks the weather is like for you, and then it needs to push back down the results. So we're going to build software that can convert input variables so that way our model can use it, actually runs the model on those, and then sends it backward. And this is really called Plumber, and I've built APIs in Java, JavaScript, Python, C#, an assortment of. Never found a language that makes making an API so easy as R. The way that you can make an API that runs locally is just these lines of code. If you have a saved model, we would just need to define a function that it would return from, start an API service, and then navigate in your browser to your local host, and you would see the results. But we'll get into that a little bit deeper. So yeah, it's really easy. You just run, if you have the repository on your computer and you're not using Docker at all, you can just run main.r, navigate to your local host /names, and then automatically you have these beautiful names that your beautiful model created for you to name all your beautiful, beautiful pets. I really like mid-nasty flace. The unfortunate part about this API that I just described to you is that it sucks. It sucks for a few reasons. It sucks because even if I made an API this way, my laptop would have to always be on. It would have to always be connected to the internet so somebody could use it. It would have to be running and available. But if you want to name a pet at 2 a.m., I can help you. My model does me no good if it can't take the jobs that come in when I'm asleep. So we need to put this model into the cloud. What is the cloud? People talk about cloud computing all the time and we never really define it, and so I'm going to go ahead and do that. And clouds are just giant sky laptops. They are someone else's laptop, but that's all they are. So we think, okay, we have our file on our computer. What does it need to run? If I was going to go to my mom, who's she's okay with technology, but not super, very of her generation. And I want my mom to be able to get pet names. I would have to make sure that we have the same operating system, that she has the correct version of R. She's downloaded all the libraries that I put on her computer, and that she opens for HTTP the whole wide world, and then she also has my code. That's so many things that she would have to download to make my code work on her machine. Not worth it. And so you could put all of this, you could start up a Sky laptop and install everything like I just said. And that's okay, but it kind of sucks. The reason it sucks is because it's time intensive. And what if 2 people want to start up my service at the same time? What if multiple people want to do that? What if I put it all on one virtual instance, one Sky laptop, and it crashes and it's corrupted somehow, and then I have to reinstall everything again? That feels like bad engineering. Because good engineering, you can almost always repeat the steps, and anything that is repeatable is programmable. So we should write a program that tells the cloud what sort of laptop we need it to spin up, what needs to be on that laptop, so that way we can actually run our code. And so that's what the concept of containers. That's the concept of containers. So containers are basically, it's a way to have less overhead, and be very repeatable instructions. So if, what's a good way to say this? So if you have one of these Sky laptops, an EC2 instance is what they're called in AWS, and that's what we use a lot on my team, so I'm going to keep referring to it as an EC2 instance. But if you had an EC2 instance and you wanted a set of repeatable instructions, so you could spin up a bunch of versions of your model at one time, that would be pretty cool. Because if one little computer could serve 20 people, the more computers that you have, the more people can use your laptop, more people can use your model. And so the concept of containers are, if every time we install this, we need an operating system, we need R, we need packages, why can't these items share those very same resources? Why can't we have one operating system that a bunch of programs have access to, but those programs can't access each other and interfere with each other? And that's the concept of a container. The container is a way of basically putting walls around your code so that way you can run a bunch of little mini virtual machines all on one bigger virtual machine. So just to make things easier, more compartmentalized, and to be able to scale the way that you want to. When I say scale, I mean when more people use it, automatically spin up more instances of your containers, so that way nobody's left hanging and nobody has to wait a long time for your model to work. This is kind of what Docker is. All Docker is a language that you use to write specific steps to set up these little mini virtual machines. So that means that you can run R and scripts created in R on computers that do not have R installed. Because in this instance, my example with my mother, if my mother does not want to install R, she does not know anything about RStudio, but she has Docker installed, I can build a container on my machine that contains R, send it to her. It will never install R on her machine, but she can still run it because it's all within the little virtual machine I sent her. And so what does this look like? There are a few words that you hear that come up a lot when you're talking about containers. The first one is dockerfile, and dockerfile is just the set of instructions that you've written. And I'll show you one in a second. You'll be like, yes, that is exactly how I would set up a new laptop. The image is the result of building a dockerfile. When you follow all the instructions in a dockerfile, the thing that's left is the Docker image. And the container is what you call it when it's running. So I could have an image that's not necessarily plugged in that other people can't access, that isn't actively computing. When it's running, we call it a container. And so this is our pet names Dockerfile, and this is really overwhelming, so I broke it up into little pieces. So at the top, we import from a different Dockerfile. It's complicated, but I'll go into that in a second. And then the next thing that we do is we install a bunch of Linux libraries that are necessary for TensorFlow to work. And then the next thing that we do is we install Python. And then we copy our R scripts to the folder that we want them to be in. We install the R libraries in the setup.r file, which I'll go over in a little bit. We open up the traffic to port 8080, and then we run our main function. And that's exactly what I would do if I was trying to get this started on a new machine. But instead, I've just written really clean, repeatable steps that any computer with Docker knows how to follow. And so this part, what do you mean that images are built on images? What I want to drill down into here is it says import from Rocker version whatever. And the first time I saw this, I'm like, I don't trust any code that I just randomly import into anything, especially if I'm building a computer from scratch. So I was like, what does Rocker version 3.5.2 look like? So I went to go look at its Docker file. And this is roughly what its Docker file looks like. It does the same thing. It's installing a bunch of Linux libraries. There's some source code. It's complicated, but as you can see, it's still just a repeatable series of steps. But unfortunately, at the very top, it imports from Debian Stretch. Debian is a Linux operating system. I have no idea what Stretch is. So I'm like, okay, let's go see what Debian Stretch is. We look at Debian Stretch, it's very, very, very small. It's just copying a bunch of stuff. But when it says this run this Debian base minimal, that's a different Docker file. And it all boils down to, at the very end of this giant rabbit hole of Docker file, tar system itself. So the very smallest executable of the operating system. And then everybody so far has been like, yeah, that, and I'll add stuff to it. And so it's like, okay, yeah, that, and I'll add stuff to it. And so you kind of get like this Russian nesting doll effect whenever you build containers where each one relies on the previous rendition. But this means that it's very easy to use Docker because you could import my Docker image, add whatever files you want to it, and it would have all the functionality that I've already built in there. So it makes it a really, really nice tool for collaboration. And so if you were to, on your computer, want to actually run the pet names and have it run in Docker, all you would have to do is make sure Docker is installed, open your command prompt, type docker build /t pet names dot. And the -t is a tag. It just lets us know Docker will generate a random name for every container that you create. Sometimes they're very silly, like 4842 hot dog. Like they have like some words, some numbers, and they're roughly naturally languagey. But I wouldn't know what that meant if I have 4 or 5 different Docker containers on my computer. Later when I look Docker, I wouldn't know what it was. So I want to go ahead and tag it and say that this is my pet names Docker container. And then to run that image, so after you, on my machine, it takes about 20 minutes to build the image. But once it's built, you can run it as many times as you want and you never have to build it again. Which is great if you need to spin up a bunch of virtual laptops because it's already built. So you can just copy it and they instantly start without having to rebuild it every time. And how you get them to run is you just Docker run rm-p. The P is defining the port, which is the 8080 that we want to go to. As you can see, that's your local host. Pet names. And then if you go to that same local host /names again, you'll see that names are being generated. Names are being generated from a miniature computer inside of your computer. And so the gist of this, the container spiel, is with Plumber in R, it's super easy to create APIs. It's like less than 10 lines of code if you've already created your model. So you really have no excuse for building models and not creating APIs around it, because it's that simple. So, okay, so it's easy to create an API. But as you mentioned, your API sucks. You have to be on your laptop, etc. So with Docker, you can create instructions very nicely. So that way you could hand a built container to your friends, or even these instructions, and have them build it on their own computer. And then those Docker images can be easily deployed to the cloud, sent up to the cloud, many copies created, and as many versions of it as you want spun up to assist with the load that your model is going to take. And so now that those engineering fundamentals are set, we understand that containers are basically miniature virtual machines. APIs are just websites. They're just websites that you navigate to in your browser. Now, hopefully, the rest of this repository will make a little more sense. And so these are all the files in the repository. It seems like a lot, especially if you're used to traditional data science type notebooks where everything's all in one giant line. To see this many files is really scary. And when we were developing this open source project, I fought a lot with data scientists on our team who really like to keep everything in the same file. And I'll go over why that is, but I just wanted to break it down for you. 4 of them are just configurations. So just short little like JSON or YAML files. 3 of them are actually documentation that you can just read. One is our open source license. And then you have 6 actual code files, which feels like a lot. But out of those 6 files, 4 of them contain like less than 10 lines of code. So first, the configurations we have the Docker ignore that tells Docker which things in your repository to ignore. This is mostly, in our case, RStudio files. So your RStudio history, we don't want it to be there. Your Git history, we don't want it to be there. Just because the less things that are in your Docker container, the less things that end up in your Docker file, the smaller your container will be and the cheaper it is to run. So small is really good. And then there's Git ignore. And that's things that we don't ever want to go into Git. So that's if you have any keys to access your cloud resources, any RStudio specific files, just kind of your dirty laundry that you don't want to share with other people. If you put it in a Git ignore, it will never go into GitHub, which if you've never used a Git ignore, it's a game changer. And then there's a Docker file, which we've talked about extensively, the repeatable set of instructions. There's another config file in there. It's a cloud YAML file. And we don't have to use it for this project, so we're not even going to go into it. But if you wanted to look into it, the Google Cloud README has more information about how that YAML file could be useful. And so yeah, out of these 7 code files, 4 of them contain less than 10 lines of code, and each file does a very, very specific thing. And this is a pattern that we've taken from software engineering at large called separation of concerns, where you really want each function, each defined piece to have one specific thing that it does. Our particular structure was based on Java, has a infrastructure called Spring and Spring Boot, and I was a Java developer before I flipped over to being machine learning. And the Spring Boot structure has always spoken very well to me because it looks the same every time I open a project, and I know where to find everything because they all have similar names. If you're looking for just data science structure, that's very good. There's the cookie cutter data science repository. You've never seen, it's mostly for analysis, not for actually deploying things live, but it just shows you how to lay out your code in a really repeatable, natural fashion that people across your organization that you're working with will understand. And if you're like me, I forget things that I do all the time. So if I bury some functions deep in a file, I might never find them. And if I need to change part of a file, I might never know where it is. We wanted to make this so that way somebody onboarding to our team could quickly look at all the files, know what they need to change, and not accidentally change something they shouldn't and really mess something up. So we'll go through each of these little baby files. There is first setup.r, which has literally 3 lines, 2 if you don't count the space. And it just says, if any of the packages fail to install, stop building the container. The reason that is because if any of the packages fail to install, the container wouldn't run. You can't run a Plumber API if you don't have Plumber on your computer. So if there's a failure anywhere, break it and let us know. And then it just lists the packages that we need. We wanted these to be separate because the more packages that you include in your Docker image, the bigger it gets, the grosser it gets. And we just want to be really explicit because it's exceptionally easy in R to get into importing things. You import tidyverse, it imports like 50 packages on the back end that import 50 other packages. And we can't have that type of cascade if we want to keep our Docker files really small. So we like to keep it all organized right there. Then there's the parameters.r. And so this is anything that you might want to change without changing the structure of your model, without even having to retrain it necessarily. And so for this, it's the one that really speaks to me is the max length of the pet name. If you think that a pet name should be longer than 10 characters, change it. And you only have to change it in this file, which makes it really easy to make little configurations, especially if this is something that's in production and you have a stakeholder that wants you to change little values constantly. This way you don't have to redeploy the whole shebang. You can just update your parameters file and everything will naturally update. And then there's the main function, which you would think would be very large, but it's not. It's exactly that plumber code that I showed you earlier, where all you do is you import the REST controller, which we'll get to. You open support 8080, and then you say run yourself. And then there's the REST controller. So the REST controller is a concept from software development. The REST is because of the RESTful API. And all it does is it says, every way that you can interact with the thing I just built, every way that you can interact with my API, I'm going to write it in a list right here. So that way these functions don't get lost in the source code somewhere else. Every single way that you can interact will be defined right here. And so what we're saying is that this little *@names says when you go to whatever URL this is deployed at /names, it will get you 20 names. So it says get generate many names 20. And it loads the model, loads character lookup, loads the max length from the parameters file, and then it returns those names back. And so that there are two more slides on this. They're supposed to be runtime functions. I don't know. So what's left? I really wish I had the runtime functions. Maybe I'll show you if I can kick off our studio real quick. I'll show you in a second. I had it closed because it makes my computer so very sad right now. Let's find it. Sweet. Okay, I'm going to switch what I'm sharing. If it will let me. Can you see my RStudio? Awesome. Okay, so runtime functions. And this is just basically where we wanted to include all of the functions that might be necessary when you're actually running this. So that generate name function, generate many names, those are all defined in this runtime function. So the generate name function here just generates a single name based on the neural network. So it what you have, whatever substring, and then it predicts the next character, and then it predicts the next character until it reaches a stop character. So yeah, while we haven't hit a stop character and the name isn't too long, continue to progress through predicting next characters. And there goes into some detail. But yeah, mostly it's exactly what you would anticipate because it's, yeah, you take the substring and then you are just adding on another letter. And then some of it's just some processing, like this is capitalizing the first letter of every word because they're names and we want them to look like names. And then this is a function to return many names, which is just says run it as many here 10 times and put back that answer because running a model that only generates one name is kind of painful because you want to see a bunch of responses. And so that's what runtime functions look like. It's just the actual code that generates the names. Okay, we're gonna pop back. Because, okay, so if you understand how to build a TensorFlow model, roughly, and you understand what a Docker container is roughly and what an API is roughly, then what do you have left to do? Well, an engineer would tell you, you need encryption support to make sure that your API is super secure. You need logging to make sure that everything that you're pushing out is absolutely correct and you can check the running container as it's actually going to make sure that everything is absolutely processed. And if you get a weird result, you can check the logs and make sure that it wasn't something weird without having to stop and take down the entire system. And engineers would also say that you need unit tests to prove that what you built is good and worthy and it works in the world. But we are not engineers right now. We're data scientists, and so we're going to skip directly to the fun part, which is releasing it and getting it off your computer so that way other people can use it. So it's been a info dump. There has been a lot of information, but we are finally saying, okay, we understand. You have a model, you've built it. How can we actually release it into the world and make it be free? And this is my very favorite part, but it's complicated the first time you go through, which is why I made the deck the way I did. I originally was going to be doing some live coding during this, but it turns out not to work very well because so much of the setup is point and click. And so what I wanted to do is I wanted to make the PowerPoint deck that I wish I had when I was doing this, that literally tells me click this button, click this button, click this button, and then do this. Even the GCP documentation, which is by and large very, very good, isn't that specific. I haven't seen anything laid down this clearly for how to get something running on Google Cloud Run. And so hopefully when you're done here, if you were to walk through this manually, it would work just, perfectly in more detail. And if you run into any problems, please let me know, because I do want to wrap this up into a blog post, hopefully, that goes over this information. Because like I said, there's nothing out there that I like that much. So T-Mobile's enterprise pipeline for releasing stuff, how it works is I'm on GitHub, I type stuff, I make a commit to the AI repository. This software called Jenkins sees, there's a new commit, automatically builds my Docker image and pushes it out to Kubernetes, and Kubernetes hosts the containers, makes more of them if we need them, makes less of them if we need them, and handles all that logic for me. This is ridiculously expensive, and I don't even want to do this for my personal projects. So this is my homebrewed free version. And we're going to use it on Google Cloud Platform, not because I'm super dedicated to Google, but because their free tier is the best. If you sign up for an account, they give you 300 free Google dollars, and that's more than anybody else gives you. And so what you can do here to mimic that T-Mobile system is you can use GitHub, and you can make a commit to your GitHub. When that commit is made, a webhook is triggered to Google Cloud Build. Cloud Build builds the image and then immediately runs it on Cloud Run, which will host and orchestrate the containers for free if you don't use that much stuff. And then for the actual building of the how do you connect to GitHub to build an image and push it out, there's this really great blog that I linked below that covers that portion, because what I'm going to be focused on is getting your pre-built container off of your machine and running on Google Cloud Run.
Heather, there was a question on what is Kubernetes?
Oh, okay, yes, I love this. So Kubernetes is, in my mind, I kind of visualize Kubernetes as like a giant octopus handling a million things at once. But basically, it's an internal cluster of computers, like a bunch of those virtual machines that has some built-in really smart logic that says, okay, so we're at 80% capacity on this container. I should spin up another container to manage that load and kind of do the load balancing for you. It's really useful if you're at an enterprise company that has to handle lots of software that has varying usage. For instance, we deal with customer call centers, and most of our calls are during like lunchtime or the morning, because that's, I mean, you all know that's when, if you have a problem during your day, lunch is a really good time to get it out of the way. So our care center is very, very busy during lunchtime. And so we need Kubernetes to sit there and be smart enough to say, I'm going to spin up a million computers to handle the load, but then also smart enough to, when traffic dies down around 5 p.m. and people are excited to talk to their families, to take those computers offline to save us money, because we don't want to be paying for any containers that we're not using, because that would be incredibly expensive. So the goal here that we're going to do is we're going to build the image on our local machine. We're going to validate that it works, and we're going to push it from our local machine to the Google Container Registry. All that does is it just says, if you built an image, you can put it here and we'll remember it. And then later, if I switch laptops and I'm still on Google Cloud Console, I can download that same image and I don't have to take the 20 minutes to rebuild it. So it makes it really nice if you switch computers a lot, or if you're collaborating with people who, for instance, if you guys wanted to download my image from Google Container Registry, that's probably what I should have done. Instead of just saying build it, it takes 20 minutes. And we're going to create a service with Google Cloud Run that what that does is it starts up the container and makes it so that anybody can interact with it. And so we're going to say build and test your image locally. If it doesn't work here, it won't work in the cloud. This is a lesson that I've taught myself repeatedly. I've always been on a cloud native team, but I hate building things locally, and I hate testing them locally, and I hate validating them. And I always think, okay, well, I can skip building it locally because that takes like 20 minutes, and I can just push it to the cloud and hope for the best. And universally, 4 times out of 5, something was incorrect and I messed up. So really building it locally is essential. And all you need to do to build your container locally is in the actual folder. So in this case, it would be in I have it named pet names wherever you cloned my repository from the beginning. If you open the CLI and you type docker build t, which is tagging it, pet names dot, and you hit enter, it will build the project. And like I said, because as you saw the Docker file, my Docker file is big, and then it reads from big Docker files that read from big Docker files that read from big Docker files. That's why it takes about 20 minutes to build, because at each step it has to stop and download all of the things from the past. If you build it on your local machine, you can run on any machine that doesn't have Docker or Keras or TensorFlow installed. So if you want to share it with your mom, all she has to do is, download Docker, which might be an overreach, but maybe not. So once you build it locally, you need to start it up and you need to actually have it running. And how you do that is you say Docker run, and then the --rm, all that says is eventually in this line, I'm going to tell you the name of a Docker image, like a specific tag that I have. And if that already exists, just remove it and replace this one there. This way you don't end up with multiple versions of the same container running that are all slightly different, that you're hitting at different times, because that would suck and you'd never be able to debug anything. So just good software engineering, write that remove there. And then P is telling you what port to open to. We want to open to 8080 because that's what Google Cloud Run likes. And then we want to tell it, hey, we're talking about the image we tagged pet names, because you might have a bunch of images on your computer for a bunch of different things. That specifically, I want you to look at pet names, and I want you to open up port 8080. And this happens almost instantly. This is not one of those big old wait steps. And then you can hit your endpoint locally. So if, as you see in the bottom down here, look, you can see that I had the meetup page open and the GitLab open, all sorts of stuff. But if you navigate to 127.0.0.1/names, because /names is what we defined as the Git endpoint in the REST controller, then names will be generated, and a big block of names will be generated, and you can enjoy them. So okay, it works locally. If you build it and you test this and you verify that it works locally, you're getting names that make sense, that's okay. And if you're looking at this and you're like, some of those are just regular pet names, you're right. Some of them are just regular pet names, because sometimes the neural network generates a name that already exists. If I wanted to make this the peak funny, what I would do is at the end of those runtime functions, I would have it go through and delete any ones that were in the original Seattle CSV and then try again. So that way I would have only novel responses. But because I'm generating a bulk of them and I'm a person that can look through and say, I know a million Louis, I didn't do that. And now is like the big part, which is finally getting this thing off of your computer. So you've built it, you understand how it's going to work in the cloud, you're going to go to that URL /names, and you understand what the results you're going to get back look like. It's like a JSON in your browser. Yeah, now that it works on your machine, it's time to spread the wealth. And I really dislike most code tutorials because they never show you what the GUI looks like, and I have dyslexia and I'm very bad at finding the right buttons. So I tried really hard to tell you exactly which buttons to click here, because that's what I always wish I had in a tutorial. So this is the Google Cloud Console, so it's like console.google.com, I think. But if you just Google Google Cloud Console, it's also the first response, and this is kind of your home base for doing anything in GCP. If you're ever lost, and I'm talking about a section that you can't find, honestly, there's this hamburger menu over in the corner that you can look down, but I, again, have dyslexia, hate searching for things. I always just Google it. So it'll say Google Cloud Container Registry. I'll be on the Google Cloud Console and I'll Google Google Cloud Container Registry and click the link. So don't be ashamed of your debugging. And so here what you first need to do is you need to create a new project. You do that by clicking this button in the top, and a pop-up will appear, and that's how you are able to actually hit the new project button and then start defining what your project is. So name my project pet names, and you have to have a project ID that's unique to everybody in Google. It has to be some character, some combination of letters and numbers, and they automatically generate one. But I was like, I'll never remember this, and I'm gonna have to type it a bunch of times. So my trick is always 1, 2, 3, 4, 5, 6 is what I give it at the end. But since I told you guys that, you guys are gonna go out and use 1, 2, 3, 4, 5, 6. So maybe come up with like a 6-digit string in your head that makes a lot of sense that you can always tack on to the end. So that way you never have to wonder what is the ID that you created. And then yeah, I don't need an organization for it. Okay, you click create. And then you check. You make sure, okay, yes, I see it says pet names up here in the top, and it has project information. I've got a notification that says, hey, your project was created. And this normally it can take about 90 seconds. I had taken longer, but there is a lag, and it gives you a little Google loading wheel up in the corner. So if it takes a second, don't think that you've broken something. You haven't. Google is just slow sometimes. So after your project is created, you have to ensure that billing is enabled. And this is because if I've been talking about how good their free tier is, if for whatever reason the API you made became so popular that you ate up all the free money, then they would send you a request asking to start billing. So in some of the APIs, they require that you have a card on file to use them. And so that's all that is you just make sure that, okay, I have a card on file. I see pet names 1, 2, 3, 4, 5, 6 is listed. Sounds good. You have to create a service account. A service account is a service account is a thing that you will create once and you will forget about it. And I always forget this step, and so it's really useful to have it written down. And all that does is it's the thing that lets you you log into it, and it's what talks to Google back and forth for you. So that way there's some authentication that's handled. So you can authenticate into Google, it knows that it's you, and then it does the talking back and forth from your CLI and coordinates the release of your actual containers. So you just need to create a service account. You just click the button. I called it pet name helper because it's helping us deploy the pet name generator. You click create. And then I like to give it the role of owner because I play it fast and loose with access. The reason I like the role of owner for this in particular is when you're doing things in the cloud, access management gets really tricky. So what have you approved this resource to access can become very, very complicated. I want this to have no problems for me whatsoever. So I'm just saying this service account, give it access to everything. So if the service account was compromised, well, it would have access to everything, which is, why people don't always do this. But I think it's fine for this case. Go ahead and give it access to absolutely everything. Click continue. And then just make sure that it's actually created. And you see the little check mark, which means everything's good. You didn't have anything weird happen. And then before you actually push the image off of your machine, you need to add another tag. And that tag is just going to say, hey, Google, look here, basically, and give Google some information about how to deploy your image. And what it looks like is Docker tag local image name. So for us, that's pet-names. And then you say where you want it deployed, the Google project ID, and then you just reiterate what that local name was. I have it set to deploy things in the US, and that's because when you think about cloud computing, all of a sudden geography and distance becomes more relevant again. If I was to deploy this in Taiwan, all of my API calls would take forever because they would start in Seattle. Well, not forever, but they would take milliseconds longer than I want, and engineers care about milliseconds. So it would start in Seattle. I would say, I want some pet names, and then it would go into the Google pipes, and it would go all the way to Taiwan. And in Taiwan, it would compute the pet names. It would come all the way back out, and it feels super wasteful. So I say, okay, use the US, please. Anywhere in the US, I don't care, but at least that way it's close, so there's not as much waste. And then you push your Docker image up to the cloud. Oh, hold on, I missed it. So what I didn't mention is this GCP project ID is the pet names 1, 2, 3, 4, 5, 6, like the one or the random one that Google assigns it. But that's why I like to use a string of numbers that makes a lot of sense to me. So that way, when I'm writing it out over and over into my CLI, I can remember it instead of having to look it up every time. And then, like I mentioned, I have dyslexia, so I get numbers swapped all the time. So it's just much easier for me if I can have it be something very simple. And so then all you have to do is say Docker push. Push is an engineering word for it's going off my computer. So we'll say push to production all the time. We're like, is it safe to push to production? And it just means like, is it safe to move it into this environment? So here we're saying Docker push pet names image to somewhere in the US in Google to this specific project ID. And yes, I mean this pet names image. So it looks like a lot of stuff, but it's actually all stuff that we can make sense of. And this takes about 20 minutes. Depending, I've had it take as much as 40 minutes, I guess, because I'm using the free tier. Google doesn't want to give me those good compute resources. And so whenever I push to the cloud, it sometimes takes a long time. Last night was one of the times that it took 40 minutes, but on average, it's about 20 minutes. And when it's pushing, you'll see it's like the cutest little ASCII diagrams. It's like equals, equals, equals with a caret at the end, and you can watch it grow longer and longer and longer. it is also really silly the amount of time that I spend just watching those carrots grow. They grow and they grow and they grow, and then finally something happens. So much of data science and just deploying in general is waiting on things to actually go somewhere. But this is the step that's saying, hey, Google, take it off my laptop. Like I'm giving you my container. And when it's successful, that's what it looks like. It'll say all of those pieces, those are the random generated names there are the chunks of the Docker image. Our Docker file is about 1.6 gigs. And so they don't want to have to send that up all at once. So they break it into pieces and send the individual pieces up. So that way it goes a little bit faster in theory. I still think it takes too long. I like everything to be instant though. And then you need to verify that your image is on Google Cloud Platform. So you just go to the container registry, which is where all the containers go. And you just make sure, okay, yeah, in the container registry, click on pet names and you see, yes, there is indeed a Docker file put up there. So now the step has been complete. Now we're done doing things on our local machines. We built it and we pushed it up to the cloud. And so now Google has the Docker file. If you get stuck anywhere on this step, there are two things that always trip me up. Number one is the container registry API enabled for your project? I just put the link there. It's very easy. When you click it, there's a drop-down menu and you can just select from it pet names repository. And that is my first step at unblocking. And then the second thing is if you haven't ever used the Google command line before, or you haven't done it this session, you need to do the auth part where you tell Google, hey, this is me. So how that works is you type gcloud auth configure Docker, and it actually opens a Google Cloud window, and you click a button and you say, yes, this is me. So that way it can tie the Google account to the person typing in your command line. And so either of those two things generally gets me unstuck. There is also, if you've authed in on an account and then you switch accounts and you don't remember, you have to revoke access from the other account and tie it access to this account. I had to do that for the very first time today. But those generally are the two things that if I can't get an image up, those are my two main stuck points. And now is the step of actually creating your service that's going to run for the world. And what I love about Google is this is the easiest way I've ever created a service. So when you go to Google Cloud Run, you just click start using Google Cloud Run. Install on GKE is installed on a Google managed Kubernetes cluster. If you were an enterprise that needed to scale this, that might be a good option for you if you want to pay for that. I don't know how much it costs to run a Google Kubernetes cluster. I know that AWS's managed Kubernetes cluster is about $20,000 a month. So unless you're looking at dropping 20 Gs on pet names, I wouldn't put it on the Google Kubernetes. I would just use the regular Cloud Run. So yeah, you click start using Cloud Run, and this is what you see. And what you need to do is create a service. And I've used this word willy-nilly all over this, but what a service basically means in software development is just a unit of compute that does something. So my API is a service. And so that's why we're creating a service here. But you might also have like a data pipeline service that takes a bunch of data, munges it, and passes it off. And so any of those individual software components we call a service. So what you want to do is you want to create the service that's going to serve up your Docker container that you already put into the Google Cloud Registry. You click create service, and you want to choose the region closest to you, again because I care about speed. And like deep learning is slow and it's not the most responsive. So the closer that you can get, the better. That's why your local machine is probably, I mean, it might not always be the fastest because of the resources, but otherwise you'll get responses the fastest because there's no delay in how long it takes the network to send the signal. Make sure that you pick a service name you'll recognize later. So I name it Give Me Pet Names because I want it to give me pet names. And then for this one in particular, I want to allow anybody to be able to navigate to this URL and see what I've created. And so I say allow unauthenticated invocations. If I was an enterprise and I had some proprietary information, I would want to require authorization to make sure that only authorized users are using this API, or if I cared about the amount of money I was spending. So that way only people I know are using the API and I've given them the right key. So that way I'm not paying for a bunch of people to DDoS myself, or like, paying for a bunch of people to use something that they don't really care about or that they don't even really want, and that I have to pay for. And when you configure your Cloud Run, you have to say here the container URL. And it's like, when I first saw this, I was like, I have no idea where the container URL is. And even if you look around, it's like, I don't know. I don't know the container URL. But luckily, if you navigate over to the Google Cloud Platform, you can copy the repository name right there, and that is the container URL. So when you get to this step in creating your service, you actually need to pop over to Google Container Registry, grab that link, and then you plop it back in. So you copy the full repository name, and then you paste it in there. And so you have pet names 12345 6/pet names. It's exactly what we've been using. And then you do want to, in advanced settings for this in particular, I mentioned the size of this Docker container is about 1.6 gigs. So you want to make sure that you have 2 gigs of memory allocated, and that just says give it 2 whole gigs. I assume it won't go over. If you select something smaller, your service creation will fail, and it will give you an error that says that it's low on memory. And it'll say you allotted 2 gigs and it needed 2.1, and so it quit, basically, but in tech terms. And so that's something to always check, is make sure that you have enough memory allocated. Most things do not need 2 gigs, and Google Cloud Run only goes up to 2 gigs, so we're like skimming in right under size limits. Oh, no. And so that's a deployment. Like, once you built it on your computer, that's all of the hard steps. Then you just have to send it up to Google with 1 line of code, and then do some clicks and start yourself a service that's now running. And if you look here, that URL, the give me pet names K465 blah 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 .app. If I copy that and then I hit enter and put it in my browser and hit enter, nothing will happen. You're like, well, okay, but nothing will happen because we didn't define a default endpoint. So if you copy that and then you put /names, you will see exactly what you saw on your local computer. Well, not exactly, it will generate new names. And so that's how that looks if you copy it up and then you put it up in your browser and you hit enter. And you can copy this one. It's still running, I believe, if you guys wanted to try it directly. I did it yesterday, I think. And so yeah, then it will display your pet names just like it did on your local computer. And that's really cool because that's a link that I can then give to you guys, and you guys can all play with the Docker image I built on my computer earlier today. And so it really works. My example is I deployed this one, which is the pet name project still. I deployed it over a year ago, and it's still up and running on Cloud Run on an account that I don't even have access to anymore. And that's how robust Google Cloud Run is, and it will stay up forever until you take it down. So it's really important, if you're not using it, to decommission your services, so that way you don't end up paying for things that you don't care about. Whew. So that was a lot of stuff, but the release is complete. That is from code to the end how you send out an API into the world. So we've done it. We've done the whole thing I said that we would do here, which is create a deep learning model and then release it to production with like little engineering interludes there. And so now what I hope is that you have the resources to define a neural network architecture in R, because you know that you can copy them, right? Like, you know now it's not a big deal. You can go out, you can copy from resources, you can copy from this repository, you know how to define a neural network architecture in R. And you also know how to train it. Like, maybe you don't know from your heart, but you can follow the train R or the train model file that I put in here and understand, okay, it's the same thing that I've always been doing. It's taking in X's, it's predicting Y's, it's splitting the X and Y data, splitting train and test, and then it's also the functions that actually create everything. So the functions that actually do the substrings and then populate through, and each time say, okay, but what is the next letter? What is the next letter? And you can create an API. That's like the 10 lines of Plumber code that I showed you that you can run locally from your computer. You now can wrap it in a Docker container, and you know what that means. So I've given you a Docker file that very well sets up to run almost any R TensorFlow API. And if you needed to add any packages and to do whatever computations you need, you just add it into that, not the parameters file, I can't remember the name, but there's the file that I showed, setup file. The setup.r file has all of the packages in, so you can just add them in there as you need. And then you can deploy it for the entire world to actually consume. which is pretty cool if you've never had something off of your laptop go. And this can be done with Shiny demos as well. So if you ever make a Shiny front end, that we do the exact same thing with Shiny as we do here. We create it as an endpoint and we release it in Docker containers. So this pattern of training a model locally, how do you conceptually put it into a Docker container? How do you conceptually make it into an API? That's enterprise software development in a nutshell, like the very, very, very simplest form, which is a lot. There's a lot to do, but also it's not that hard. Software engineers talk all the time about how hard their jobs are. And it's easy to even look at this presentation and say, well, we didn't encrypt it, the endpoints aren't secure, there's no logging. But frankly, like if you're a data scientist, you're out there and you're writing code, and code is just code. So you can write software development code too. And in fact, you can write software development code in R and not even leave the programming language that you like the most, and have that be released and have it be scalable and performant, just like everyone's Java stuff, you know. And so what is next for this? I've given you the world's quickest rundown of what our enterprise projects look like and how we end up deploying them somewhere. And so to my manager's name is James Ellison, and he has this quote about how we operate for finding work on our team. And he always says, find the gaps and fill them. Like if you don't know what to do, find the gaps and fill them. And so I hope that with this presentation, you at least learned what you don't know yet and have some pointers to really good resources where you could go and begin to actually dig into that information and learn all those things that you don't know. Specifically around the API creation and Docker stuff, I have some blogs on Medium that are under the username Timotech, T-M-O-T-E-C-H, and they walk through that very, very succinctly, but the code here is also very well commented, and you have this entire PowerPoint deck. So you have like 4 different resources and you can triangulate yourself between them and figure out what you don't know. So that way, if you do want to get things deployed, you know now that you can at least learn it. It's all right here. And so with that, I wanted to say thank you everybody for tuning in. And I can answer questions if there are any questions, but it was really, really, really a lot of material.
Okay, so in our CEO's old-fashioned state where he like gave out money, we are giving swag for the first question asked. I already rewarded somebody with a swag. So next question, anyone interested in asking the first question after this presentation?
So, and specifically what our CEO would do is he would hand out $100 bills. So this is like in the spirit of handing out a $100 bill for the first question, because it takes a lot of bravery to ask a question.
Clothing off his back.
If nobody has any questions, that's totally okay.
I have a question, but I'll just be a zero question. So in your team at T-Mobile, which tools are you using for scaling? I'm assuming you're using Kubernetes and AWS?
Yeah, so our Kubernetes environment is deployed on AWS right now. And so, but we did look into using AWS managed Kubernetes. It's just they charge so much. and we have, so the AI team is really lucky. We have an entire team dedicated, not just to us, but to a few teams called engineering efficiencies. And the engineering efficiencies team is the one who sets up, like, as soon as we commit to Bitbucket, everything happens. And all of our package management. And we have some really complicated, if you know anything about Kubernetes, you have some really complicated like init containers and like ingress logic that all has to be done to make sure that everything is incredibly secure, because we don't mess around with customer data here. And so they help us do all of that sort of stuff. But then as far as analysis is concerned, we do it all on our local machines. And if we need a GPU or something really big, we use Core Scientific's platform, because Core Scientific is a company that gets NVIDIA GPUs as soon as they're released, whereas AWS, Microsoft, and Google Cloud take 6 months after they're released to actually get the new NVIDIA software. So to use the most current GPUs, we use Core Scientific's Plexus platform. Oh, and then, yeah. Does that answer your question?
It does.
And then we have one from the chat. It says, when you talk about the nested dolls of Docker containers, are all those layers necessary, or would it be better to have a smaller amount? Yes, so this is a great question. And the thing about this that's really nice is, like, of course, it's best to have the smallest amount possible. And we actually had a problem whenever we built our first R TensorFlow API container, because the version of Rocker that we imported contained all of our studio, and it also contained all of the tidyverse packages. dplyr itself is like a gig. And so what happened is, I was deploying R under the covers. I hadn't told our engineering efficiencies team that we were going to be doing this, because I didn't think it was any of their business. It's just a Docker container. And eventually our lead engineer came over and was like, Heather, you're breaking everything. And I was like, what? And he was like, the past week, you've been breaking everything. What are you doing? And it turns out that our containers were almost 5 gigs, which was above, way above the 2 gig limit that our cloud asks for. And so our containers were actually knocking things completely offline by, like, taking down the whole cluster and using up all of the memory resources. So everyone else's containers were dragged down with my ship. But what we were able to do is, by being very specific about the things that we install, we were able to get that size smaller. And that's why there are so many lines, is I think that like so many lines of code, because there are all these very little Linux packages. And I think that everybody who has been me has gone through a similar step, where you once had a Docker file that was like 6 lines and it was beautiful, but the image resulting was so big that you then had to go and pull out all of the fluffy bits that you really like tidyverse and dplyr, to make it very streamlined, and then you're left with raw Linux libraries. But yeah, in general, the smaller the better, but you don't need to be worried too much about the complexity of a Docker container, because once it's built, it can just run. So, like, yes, it would make the build time slower, but I only have to build 20 minutes one time and I can deploy a bazillion. And so it's not as much of a sunk cost as if it was a function running slowly, and then every time someone hit the API, it would take longer. It's only that one hump, so we kind of deal with it. And then I guess also Jenny gets swag.
Hey, Heather, this is Sean. Can you hear me?
Yes.
Hey, thanks for a great presentation. That was a really awesome overview. And thanks for the link to the repo. That was cool. I have a question for you about, so obviously you did this in R. Do you do all of your neural net stuff in R, or do you work basically primarily in R? And can you use this? Sorry, go ahead.
Yeah, our team is bilingual. The interesting thing about the R ecosystem so my R versus Python thing is, the thing about the R ecosystem that I like is, when you install packages, they really work like you expected them to, because the CRAN is there as a giant gatekeeper saying, what's our quality look like? So in general, we have less trouble actually getting the R stuff to deploy than the Python, because Python, like, the package management can get so tricky. That being said, sometimes R can't do all the fancy things that we want. So we have a set of custom embeddings that we made, and we did that using PyTorch and Python, and they are beautiful embeddings, and now we can load them in R. But yeah, and then the other thing is that, by and large, the hardest part of doing deep learning in R is getting the Python to work with R. Like, getting those two things to talk back and forth sucks. But yeah, we're right now, we used to be primarily R, and then we switched to mostly Python, and now we're like directly down the center. But our giant, like, topic model classification, that's like our big heavy hitter, that's an R.
And the plumber, I was looking, you can use either Python or R with all the plumber tools?
Plumber is an R package. If you were going to do an API in Python, we use Fast API, but there's also Flask. But Fast API seemed to be the quickest, nicest, most plumber-esque way of doing it. You could make a plumber API using, RPy, to talk to the R from there. The downside of plumber is that it doesn't allow HTTPS traffic. And so if you want to get into how to make Plumber accept HTTPS traffic, what we actually do is, inside of our Docker container, we build another Docker container that just runs a Nginx server, and it accepts HTTPS and immediately converts it to HTTP and talks to the Plumber service.
All right, thank you.
You're welcome.
Hi, I had a question. So like now you presented before us the whole end-to-end process of, the analysis and then loading it on cloud. Like every member in your AI team has to go through the whole process. They have to deploy it on cloud. Like each and every member is a part of that.
We do have every member deployed to the cloud just because I think it feels so powerful to be able to do that. We do streamline the process a little bit. So if you're internally doing it, you do have to do all the Docker and you have to like make sure that it works locally. But then you don't have to go and click buttons and set up a config file. We have that all set so computers automatically do that. So you just commit it and then you merge it to the master branch. And every time you merge to the master branch, it kicks off a build and deploys it. But then we do have them do the validation too. The data scientists, anytime that they're doing a release, we have an engineer or a machine learning engineer be with them to do it. But I think getting data scientists to release into production and build quality code that makes sense is the quickest time to value for an enterprise, because how it traditionally works is you have one team build models for forever and then they pass it off, especially in R. You have team build models in R and then they pass it off to another engineering team that's going to redo it in Python, and then they redo it in Python, and then they pass it off to a team that creates the API who passes it off. And I'm on an extremely agile team. So the AI team spun up out of a team called Social and Messaging Product Development. And what it did is it builds the pipes that allow our call center reps to talk to customers on like Twitter. So like, how do you connect to Twitter and funnel all those messages and eventually get it to a call center rep? So we were sitting on all of this data that flows between customers and a call center rep, all of these transcripts of these care conversations. And so I was really lucky I was an engineer on the team, like a Java developer. And when they said, hey, we want to start doing stuff with these transcripts, I was like, hands in the air, me first. And they were like, what did you do to deserve this? And I was like, I spend all of my time building natural language Twitter bots because I did at the time. And they were like, oh, okay, if you can do that, then you can do this. And so that's how I rolled over. But yeah, we're a heavily, heavily engineering team. Sometimes we do have data scientists join who don't know that stuff. In fact, almost all the time they don't know any of that stuff, but we're really patient and get them up to snuff.
Wow, thank you for answering.
You're welcome. Okay, so then the next question I see is how do while loops in container? So I would say it's not even a while loop. It is something else. It's very akin to a while loop, and you can think of it, but basically when you hit run on that and you open a port, basically what it does is it just says, I'm listening, and I'll keep listening until I hear something, and I'll just keep listening until I hear a response, and I'll continue to listen, and then, oh, finally I got a response, thank you. Now I'll process it and I'll return it back, and now I'm back to listening. And that's what it means to open a port. I like it because there's a beautiful analogy for like an actual country. Like the whole United States doesn't need to be watching the port of Seattle. The port's always open, and when boats come in, we say, oh yes, let's go and let's address this new shipment that we got, and then we'll go back to doing our business. Does that make a little bit of sense? Okay, awesome. And then this says, oh, how I came across my internship and strategies to find something similar. So how I came across my internship was actually really funny. I was looking for a bunch of internships, and I was interviewing at a T-Mobile position in California somewhere, and I interviewed at Zillow, and I interviewed at a few other places, and for a strictly software development job. And my wife and I built this really ridiculous website that's now gone called Tweet Mashup. What it did is it just hit, if you wrote, I really like dogs and dogs love walks, it would join on the word dog and say, I really love walks, which seems silly. But when you start combining very famous people, it gets very funny. So like Hillary Clinton and Elmo might join on the word apple and write something really weird together because the beginning's in Hillary Clinton's tone and the last is in Elmo's tone. And we were supposed to give a talk about that. Like Twitter asked us if we could do like a Seattle meetup and give a talk, but I was in grad school and I was like, no, I have class in the evening, so I didn't get to go. But my wife went and she presented it and she gave the talk, and it was very good. And after that, the T-Mobile team presented, and they presented about some customization work they had done. So that way, even when you're DMing with the T-Mobile account on Twitter, you would be able to see an individual representative's icon. So the icons could change per person operating behind the Twitter account. And they presented on that information. When my wife went over and was like, maybe my wife will end up working with you. She's interviewing at places. in California, and they were like, we don't work in California. And they're like, what? And so Jacqueline was like, whatever, check out her Twitter. If you like her Twitter, you'll probably like whatever she does. So then after a few days passed, I saw that they followed me on Twitter. I DM'd who is the guy who's now my current manager, who at the time was ended up being my product person, and said, hey, I hear that you're looking for an intern. I love Twitter. I love building Twitter bots. I love the Twitter API. Can I interview with you? And I interviewed, and Michelle was actually the recruiter who interviewed me. And so we both moved on to different jobs since then within T-Mobile. But yeah, and so I would say like straight up Twitter. And it's not like the answer that everybody wants to hear, but it's so much easier for me it's so easy to get a good sense of who's talking to you and to have an honest conversation that's not super business polished via Twitter in a way that it isn't via traditional communication channels. And I obviously liked the team that I got matched up with so much that I stayed for forever. So it's really good that I didn't go with the team that was in California. But yeah, I always recommend Twitter now.
Can I ask a more general question? Yeah. So, for example, I know T-Mobile as a service carrier. So let's say my phone has T-Mobile carrier, but then how does your team relate it, like, or affecting my day-to-day life? Or like, how does this project relate it to, like, what does T-Mobile do?
Yeah, so my team right now is focused mostly on care. So all of the products that we build go to our front line. So if you ever have a problem and you call in, we are using AI to try and solve that problem as fast as possible. The reason that we don't, a lot of companies build like chatbots that they insert in front of people, and we don't really want to do that because at T-Mobile, we really value the person-to-person communication. And so our goal with AI is to bring all of the information that is possible to the representative in the most targeted and filtered fashion to actually solve your problem. So that way you don't have to wait on hold for like 58 seconds while they Google something. But we've done some stuff in the fraud space too. So like people doing fraud, how can we tell when fraud is occurring using AI and some things like that. But eventually my dream project has to do with network towers. You can tell when a network tower is about to go down and begin to reroute traffic into other places. It's a very operational research problem, and I don't have enough experience to necessarily spearhead that myself, but I think that there's a way that we can use artificial intelligence to make our network more stable by routing those calls to towers that are really healthy without waking up engineers in the middle of the night and making them do it themselves.
So are you saying like the project or your dream project is something more like a network tower health monitor in terms of like using artificial intelligence to kind of monitoring that?
I think monitor, and then also once you've discovered that something's unhealthy, how do you choose which calls to send to which new towers? Right? Like there's a huge problem. Yeah, like I could send it here, but how does that affect the downstream, et cetera? Like it becomes like a giant network problem. And I think that would be awesome. And it gets us out of the natural language space because we've been chomping on natural language for a while now.
And also in our team, so we're working on this project right now where we're putting IoT devices on the data centers that are taking in the calls. So there's a data center between the cell tower and the outgoing or incoming caller or data usage. And we have the IoT sensors that are basically doing constant monitoring on those data centers, that we have dashboards that show these are going to go down. We can predict which data centers are going to have problems all the way at the rack level. So that's a project that our team is working on. So there's a lot of applications for AI and ML at T-Mobile. We do a lot more than just phone service. We have supply chain, we sell phones, we do device financing, we give loans to people for devices. We work business to business. We have now business with government, a lot of government contracts with the Sprint merger. So it's actually, there's a lot more out there than you might originally think. Every day I sort of learn about new groups or business teams within T-Mobile that are doing something cool with data.
I think that's a good one. Yeah, when you were talking about all those different areas of business, I was reminded of T-Mobile Money. We're a bank now too, like, yeah, all sorts of different things. And then Okay, you're welcome. And then there's a, is it common for the APIs you build to return a simple return like this, or is it a more complicated UI? I would say they always return something simple. In fact, the list of results is probably too complicated. If I was building it for work, it would only return one thing most likely. And the reason that is because generally my model is part of a larger ecosystem of software. And so you might have like a Java service that's listening to what messages are coming in, and that Java service compacts the conversation, and then it sends that conversation to my model, which returns a topic. And then that Java service says, okay, now that I know the topic, I'm going to send it to a separate Java service, which will then format it correctly and send it to a UI that's in some place somewhere else. But that UI even just reads JSON and renders based on the JSON only. So it's always some sort of stringy output.
Very cool. Thank you.
You're welcome.
Cool. So are there any other questions for our analysts or data circles?
I just wanted to know, will the video be shared and even the PPT that was presented? That would be very helpful.
We will share it out.
Yeah, the PowerPoint should be in the repository already. I committed it like at 3:30, so right before go time basically. So you can download it from there. It's like 90 slides, but Michelle did record the video.
So that be shared, like that be emailed to us, or I don't know, what should be the other source to
Yeah,
the
it will be shared.
recording again?
It will be shared with you for sure.
Thank you.
And then yeah, like I said, if you reviewing this later, you have any like questions about literally anything, I've touched this stuff so many times in so many different ways. And as I mentioned at the beginning, the pet names project is like a simplified version of what we actually use in the enterprise. And so there's always, if you want to make it more complicated, I know 1,000 ways to make it more complicated.
All right, perfect. Thank you everybody for joining. And like I said, if you have questions at all, I did send information in the chat, as well as you can reach out through the meetup. So thank you so much for joining. We appreciate it. Take care. Have a good day.
Bye.
Bye.
Thank you guys. Bye-bye.